Good night, everyone. As promised, I'm going to do an example of the project due for the end of this term of the underground water tank made of reinforced concrete. I'm going to send you this. This is basically a sketch of a sketch of what I envision my tank to look like. This is the main area of the water tank, and you have the pump room in this corner here. In elevation, it's 5.5 meters deep. The area of the tank is 20 meters by 10 meters, and the area of the pump room is 3 meters by 4 meters. Design considerations: the beam section is 500 by 250, column section 250 by 250, wall thickness 450, floor thickness 750, cover thickness 300. Now these are not calculated, these are just what I think that the dimensions should be, that should be sufficient when you run your analysis. If it fails, then you make your changes as you go along. Alright, so let's start. New project. I call mine draft class. Make sure that the configuration is in metric, because we'll be working in metric. Meter, kilonewton, okay. Alright. Instead of using the grid, I'm going to start installing the nodes, placing nodes. So geometry, and we know we're going to start at 0, 0, 0. Looking at the drawing, I'm moving in the x direction. The next spot is going to be 20, 0, 0. And above that, it's going to be 20, 5.5, 0. Actually, this one should be 0, 5.50. And this will be 20, 5.50. You have to have a good understanding of your UCS icon, where Y is and where X is and where Z is. As well, and what we could do to make this easier for you all, I will delete these steps here, and I'll also delete this node. Alright, so these are the 0, 0, 0. 0, 0, 0. I'll go up 0, 5.5, 0. Using the node cursor, I'm going to copy this in the Z direction 10 meters. I'm not linking anything. I'm going to select all of this, copy it 20 meters in the X direction. This node here is 3 meters down, so it's 3 meters in the Z direction. So the node would be 20, 3, 20, 0, 3, 20, 5.5, 3, 23, 0, 3, 23, 5.5, 3. Let's see. Next part would be 20, 0, 7, 3 and 4 is 7. Then 20, 5.5, 7. And then 23 right here is going to be 23, 2307. So 2307. And it's going to be 23, 5.5, 7. I hope I'm getting this right. If I made any errors, then I'll change it. Alright, let's connect the dots. Oops, this is wrong. It's 23. Alright, let's connect the dots. So go to your connect beams and we'll just do the top. Just select 20 and this one is 23, so it seems okay. And connect from here to here, from here to here, here to here, here to here, here to here. You should notice what I'm doing. And if you notice, I'm not connecting the base. The base is a plate, so I don't want any connection here. I'll create a arm. Yes, save. So I'll create a plate at the bottom here, but not now. So you should see it starting to form. Create a beam across here. Okay. Now the top plate is going on top of here, and this span is 20 meters, but in actuality, yes, the span is 20 meters, and then you have a small plate here, and it's 10 meters here. So I would like to divide this in 5 meters increments. So I'll select this beam and this beam, go to geometry, split this beam, and cancel. Let's do it just one beam. Geometry, split beam, right. Add new point, yes. Oops. And the distance is going to be 5 meters away from the end. At that point, and it's going to be 10 meters away from the end. At that point, it's going to be 50 meters away from the end. Add new point. Right? Okay. Using your beam, your cursor, control, select these three and copy to the Z direction 10 meters, and you can link it. Okay. This beam has to split, so geometry, split beam, midpoint, and we're going to copy this beam in the X direction 20 meters across, and we link in the steps. Okay. So now you can see how easily I created the beam system and the columns. Now we want columns as well here. So then we copy. Oops, these. Oops, we need to split this beam as well. Instead of doing that, let's delete this beam. I want to make things as easy as possible. So, and we will copy these three nodes to the center in the Z direction at 5 meters, because 5 meters is the midpoint of 10 meters. And do we want to link the steps? I'm not even sure. Yeah, I think we may want to link the steps, but it's okay. Alright, that's fine. And then we can now draw and we want to copy all these nodes I want to copy all these nodes except this one down 5.5, negative 5.5 to create columns. So you should see it starting to form Alright? What can we do? Can we start creating the properties? Or shall we create? Let's create the properties. So the properties or the beam section was 500 by 250. So we go to define rectangle, and the y direction was 500, z direction was 250. Add 250 by 250. Add, close. The thickness of the plates, the wall thickness was 450, so that's 0.5. Add, and the floor thickness was 0.75. Add, and the cover, the plate on top was 300, but we're not modeling that, so close. So for the beams, you go to select, make sure you select the beam first, select, beams parallel to the, select beams parallel to the x direction, select beams parallel to the z. Assign to selected beams, assign, yes. Now we want the columns selected, select beams parallel to the y position, and assign. Alright, we can leave this here for the hour. Now we want to create the plate. So to create the plates, add 4 noted plates in anti-clockwise direction. So should be familiar with this step. Let's ensure that you're creating it in an anti-clockwise direction. You can use your arrows to rotate. I think there's a wall here. Yeah. Spin it around. Just ensure that I'm not copying. Alright, so there are plates here, plates here, plates here, plates here, a plate here. Oops, I missed a spot. So let's create another one. That should be it. No. Plate here, plate here, plate here. Should be a plate. Oops. Plate in this location, right? Plate in this. See, we're missing a plate here. So we have a plate here, plate here, plate here, plate here, plate here, plate to the back, plate at the side, plate to the front. Right. So before I model the floor, I just assign which thickness it was. 0.45 was the walls, so I could just say assign to view, and assign, select all the plates. Now to model the floor, which is this. So I want to do it from a bottom view, and anti-clockwise. Try to do it from a top view. think the better thing to be safe is to select the nodes at the bottom, create a window, look at it, make sure, right? Create a section cut. Let's look at it in top view, and then now we could create two separate and create this one. Okay, and one time let's assign to this view. So now we have two plates, right? So plates for the wall. So we have done the properties. All right. Now mesh. So we're going to mesh. We're going to assign generate plate mesh. I'm not going to generate this plate mesh. I just want to see how much to mesh. So it's going to be 5. I'm just going to keep it 5 right around. So I'm going to select all my plates, be it parallel to the XY. Right. All those generate a new mesh. Mesh. And it's going to be 5, 5, 5, 5. Give example. Quadrilateral. Right? And then let's see how much generate plate mesh, quadrilateral. This is the same thing. So select plates parallel to the YZ, right? And generate the plate mesh, and it's going to be 5, 5, 5, 5. Quadrilateral, okay. Now to do bottom. Actually, let's just do the bigger piece first, which is about here. And generate that plate mesh. And that's going to be 20, 10, 20, 10. Apply. And then let's select let's ensure that we are selecting just that one. Generate plate mesh, quadrilateral. And this is going to be 3, 4, 3, 4. Apply. So all the meshes, all the geometry, everything is meshed. Next, we're going to load the boundary conditions, create foundation. It's a plate in the Y direction, 95,000 subgrade modulus, none add. Let's look at this. Select plate cursor. Select all the plates at the bottom. Let's do that again. Assign to selected place, assign, yes. So we can close that off. Right? So we're looking good. Let's look at this in general. Whoa, what is this? What is this? What did I do? Whoa, what is this? That's... Oh, I see what I did. This was 0.5, but be very careful with the units. Change, close, edit, 0.25, tab 0.25. Make sure that your units are correct. Alright, and let's generate it again. Alright, it should work now. So looks beautiful. This is the tank. All the supporting beams and columns and plates, everything is meshed. We're good to go. Next is loads. So the first load and the simplest load is going to be the self-weight of the structure and also the plate on top. Now the plate on top was 300 millimeters thick. So I've created an Excel spreadsheet where I created all these parameters, and it's 0.3 meters on top, thickness on top. So to determine the weight, the dead weight of the plate on top, you can say self weight of cover plate is going to be equal to the thickness multiplied by the weight of concrete. I need to put in what's the weight of concrete. So thickness, weight of water. I can put it right here. Weight of concrete. Assuming that the concrete is 4,000 psi. Yes. So the density of concrete is 2,400 kilograms per cubic meter. So the self weight is going to be equal to the thickness, the assumed thickness of the top slab multiplied by density of concrete divided by 1,000. So let's put this in brackets. Divided by 1,000. So 0.72. I like to round off, so round up to the nearest decimal, 1 first decimal place. So a few arguments. What did I do? This is a number. Round up. 0.8. That's the total weight. Kilograms per meter square. So this will be kilonewtons per meter square. Alright, so we have the self weight of the concrete. So going back. Yes. Going back to that, now we're going to create our load cases. So first we add our dead load. Keep it in caps. Dear dead load, add. We're going to have the water in tank. That's going to be a fluids. And then we're going to have soil pressure external. You could call this anything you want. And then we're going to have the uplift from the base. That's the soil as well. And close. So let's deal with the first one. Gonna add its self weight. Now if you notice, I'm kind of breezing through because the previous videos will have explained all of this. Add, and then we have a floor load. Because we did not model the top slab, the pressure was, the load was, you know, when I think about it, I think I was not supposed to divide by 1,000. 720. Yeah, just returning, I made an error here. It's really 24 kilonewtons per cubic meter multiplied by 0.3 meters, and that'll give me 7.2 kilonewtons. We can round this up as 8 kilonewtons. So we'll put the pressure as negative 8 kilonewtons. And the range is going to be, so since this is 5.5, the minimum is going to be 5.5, and the maximum is going to be 6.5. Because it's, no, it's not 6.5, that's too much. Minimum will be 5.5, and the maximum will be 6. Right? Global Y, not one-way distribution. Add, close, see if that works. Right, so that works. And the self-weight that's assigned to view. So that's taken care of. The water in the tank, we have to determine what is the pressure acting in the hydrostatic pressure acting in the tank. And I did this with the weight of water. So the formula is half water pressure in the tank is equal to, rho GH, where the weight of water, G, C8, Ka, which is the coefficient, the active, right? It was 30 degrees, so it's going to be 1 minus 30 degrees over 1 plus 30 degrees, will give it 0.3. That's the active coefficient. So the water in the tank is going to be the active Ka multiplied by the weight of water multiplied by the height, and in this case is 5.5. So the water in the tank, pressure in the tank, is actually equal to 0.023. What did I have before? I had 6 meters. 0.02, so now it's 5.5. So this is 0.024 kilonewtons per meter squared. Okay, I'm back. I may have made some errors with my Excel spreadsheet, but it didn't save, so now I just went back to make sure that I had the proper units. So let's open about this. Where were we? We were going to put in the loads, the water in the tank. So the water in the tank, water pressure in the tank is going to be equal to the density of water, rho GH. So it's the density of water multiplied by the gravity multiplied by the height, and we divided by 1,000 to make it kilonewtons, and we rounded it off, so it was 54. So I'm going to add plate load, hydrostatic, and remember the water is in the tank and not out the tank, so make sure your plate cursor is selected. This is going to be negative 54 kilonewtons per meter square. Y interpolate along the global x direction. Press add. Just to make sure I'm picking up the right. I think this plate here. There's no plate here, so this plate. Probably this plate. Let's look at it in 3D. Right. So this plate will be positive because it's acting in the positive global x direction. So press add, close, so it works, it's fine. let's add in the Z direction now. So using this view, add plate loads, hydrostatic. This view is going to be negative 54. Interpolate along Y, but in the global Z, add. And I think it's here. It's not there. I think it's there. Let's just double check. Nope. That's not what I want. So go back to that field. I think the easiest thing to do is to switch it up and let's select this. Let's see what that looks like. Yeah. Alright, so it's going to be positive 54. Y global Z, add, close. Let's see, that's, yep, looks good. Yeah. So we have the water, but we also have the water acting on the plate below. So make sure you select just these places, because in this area there's no water. Right, so the water is acting down. So again, water in tank, add. But in this case, it's acting fully down in on the negative Y direction. So global Y, add, close. So assign to selected plates. Assign, yes. So that's the end of that. So now soil pressure external. We calculated. Now the soil pressure is going to be equal to the surcharge, uniform surcharge, plus the active soil pressure, plus the water pressure in the soil. F2. So the soil pressure, active pressure is equal to the height of the stem multiplied by the weight of the soil multiplied by the coefficient. So that takes care of that. We have the uniform surcharge, and the water pressure in the soil is equal to half gamma G, no, half density of water by H squared, right? I have to go back in the notes, but it's going to be half the density of water by the depth squared. And when I added all of these values together, which is the total active force, is equal to the sum of the uniform charge plus the water pressure in the soil plus the soil active pressure. I would like to round, let's see what the value is. So the soil, the total active pressure is equal to 26 kilonewtons. So soil pressure plus add, and this is going to be on the external, so plate loads, hydrostatic. Let's start with each plate here. It's positive, and the value is 26. So 26, interpolate, 1y, global x, add. We're gonna have, so sorry, these here. I'm gonna add those. No, that's negative. It's gonna be negative 26. Add. So that's that, but I need to select these here and these here. Oops. Let's do that again. Just pick thumbs. Be careful when you're picking. Aye, it's really tough. And then, right, that works. So much of it. This is also negative 26 in the global X. So add that. And then let's go to the top view. Then we have on this side, it's going to be positive 26 in the Z direction. Add that's going to be negative 26 in the global C direction. Close. So let's see, it's working. It's on the external, but that's what we wanted. We also have to take in consideration the surcharge that's on top of the plate. So it's going to be plate loads. It's going to be a full pressure plate. It's going to be negative 5. Actually, no, it's going to be a floor. It's going to be a floor. It's going to be a floor load because we can't model it. So it's going to be negative 5. And the range. Now, the wall is 5.5 plus 0.3 for the slab. So the minimum is going to be 6 meters, and it's 500.5 meters below grade, so let's say 7 meters is the maximum. Global Y, add, close, let's see if it works. Cannot generate load for command. So first of all, look at this now. Edit. Minimum is 6. Maximum is 5.5, 6.5. Change. That works. Alright, so now we have soil load acting on top of the structure. So that takes care of the third condition, loading condition. And the last one is the uplift. We have to decide to design the uplift value. So let's do that. Right, so the buoyancy pressure is equal to the area of the bottom slab multiplied by the pressure of the water acting below the slab. So the water pressure is going to be the head by the weight, the density of water. Correct? Yeah. So the depth of the water table is 4.75 meters in this case, because it's equal to the height of the stem minus the depth from grade, which was 750 millimeters, and the area of the base is equal to the length of the base by the width of the base. But in this case, No. We also have, if I look at it from a top view, this is different. Now, the excess sheet I created was created for something, for my design. So let's look at the dimensions. So it's 20 by 10, and we have 3 by 4. So it's 2 areas we have to look at. So length of base. So let's add a couple of lines here. Let's call this length of base 1, width of base 1. Right, and length of base 1 was 20, and the width was 10, and the length in this case is 3 and 4. So it's meters. Oops. Meters. So the area of the base is equal to the sum of that plus product of these two here. Which is 212 square meters. So the buoyancy pressure, which is equal to area by pressure, is equal to the product of the area of the base multiplied by the density weight of water multiplied by the height of the water depth, which is 4.75. All of that is going to be divided by 1,000. Oh, buoyancy pressure is so high, is it? That's high. Yes, I'm back. What I realized is that what we were calculating before, will give you our actual force and not our pressure, because pressure is measured in kilonewtons per cubic meters. And the weight or the density, it was PCF. This is actually PSF. This would have been Kn m squared multiplied by the area, which is m squared, which would have given you Kn. But what we could do is just do a full pressure of 12 kilonewtons at the base of the slab. If I'm wrong, you all could send me comments. But I think I'm right. So the uplift, let's put this in perspective one time. Uplift is going to be a plate load, pressure on full plate. It's going to be 12, so it's positive because it's going up. Global Y, add, close, and let's select the full. Let me remove this. Right, it's going to be everything at the bottom. Right. And assign to selected plates. Assign, yes. So that's at the bottom. Alright, so that's my 4 load cases there. So what I'm going to do is I'm going to create load combinations. And this one I'm going to call tank full. We'll be ignoring the soil pressure on the outside. So there will be the what cases. I'm not sure what the factors are. We could always change it. And then the next one will be the soil around the tank. You can add that. The last one would be the uplift, so it's going to be the dead load and the uplift. I forgot to change these names. So this one is going to be soil caps and soil pressure. Soil pressure. Change. And this one is going to be uplift case, I guess. Let's call it case. Change close. So we have our combinations. This is what we're really interested in. So let's run our analysis. I think we should be good. Don't usually go into tools, blah blah blah, check multiple structures, all check nodes, check duplicates. But I think we should be okay. So you go into analysis, add, close, and then you go into analyze, control F5, save. Let's hope we don't get any errors. No errors, no errors, no errors, no errors. No warnings. Looks good, looks good, looks good, looks good, looks good, looks good. So that's it. Next time I will do the reinforced concrete design. Alright, so good night, bye.